So to open the Treble platform, I go to app.treble.tech. First I have to log in. I've already logged in. And what I'm faced with here is an overview of the different projects that I've been working on. A project can, for example, be a school, and then a school building will have different spaces within the building, which I'm designing the acoustics of. So for example, a particular classroom, another classroom, a meeting room within that school. Same for a hospital or office building or whatever. And today I'm going to play a bit around with this model here, this space, which is a part of this office building project. And I go into the space here, and then I'm faced here with kind of different revisions of the geometry of the 3D model that I have been playing around with. So I will just open here one I've already uploaded, which is called the initial design. I gave it that name. Okay, and then I open the thing here and I go into what we typically call the editor. In the editor you can view the 3D model and move it around and things like that, and you can then set up your simulations and run them from here. So let's create a new simulation, and I'll just call it initial material configuration, something like this. And now the first thing that I have to do is I have to assign materials on the different surfaces in the space. When I prepared my 3D model, I divided some of the surfaces onto different layers to sort of facilitate the material assignment later. I can assign materials on an entire layer or on a surface within a layer if I want. And let's then open up the material library. As mentioned, it's a very extensive library of materials that we have sort of carefully crafted with impedance information and everything. And if I then open up a particular material, maybe let's open one interesting, something like this one, then I can open the detail view of it and see here the absorption characteristics, but also the complex reflection coefficient, which is related to the complex surface impedance. I also have some details about how this material was crafted. Okay, I can also create my own materials here, where I input absorption coefficients and then I give it a category as well. And the category plus the absorption coefficients is used by this algorithm I mentioned earlier to convert the absorption coefficients into a physically plausible surface impedance. All right, but let's just try to assign some materials here. Let's start with a glass wall. That's a window material. So I will put a single pane of glass on the glass wall. I also have a layer here called windows, which is the sort of outer windows, and I'll put a double layer glass on that one. Okay, and then let's move to the tables here, maybe in the furnishing or the wood categories. And yeah, I have a material here called wood. Let's just put that one on. Doors, maybe this hollow core door material. Chairs, how about if we put leathered covered upholstered chair material on the different chairs here. And cabinets, maybe that's plywood paneling 1 centimeter thick. And I think that's it for these two categories. The ceiling, let's start with the hard ceiling, so no limited acoustic treatment in this space. Let's say rough concrete here. And the walls, maybe they can be gypsum boards, something like this. The floor, let's use the search function here, put linoleum on the floor. And the monitors, how about if we just say they're 40% absorbing, frequency independent, as we see here. All right, next step is that I have to assign scattering coefficients. So the scattering coefficients are only used by the geometrical high frequency solver, which is sort of an indication of surface roughness. And the tool proposes some scattering coefficients based on the material that you've selected. In some cases that's a fine choice, but in other cases you might want to modify them a bit. And I'll just modify a bit here, maybe up to 0.6. Let's say the cabinets are also a bit more diffusive, tables as well, something like this. All right, now the materials are set. Next step is to set sound sources and receivers. So I will put a sound source in here. Let's give it a name. Cool source, and let's move it around. So let's drag it all the way over here. This is our first sound source. I can open the detail view of the sources where I can select directional sound sources too, such as speech or given loudspeaker. As mentioned, we are growing our library of sound sources as we speak. But for this test here today, let's just use an omnidirectional sound sources. Okay, let's add a couple of more sources as well. Maybe one in the corner here and one somewhere in the middle of the space. Something like this. And then let's add a few receivers. Maybe first one here all the way in the corner, second one over here, or let's maybe have that one be kind of sitting here by this desk. Should we put it a bit down? Something like this. And the third one in the corner. Something like that. Okay, materials, sources, and receivers are set. Last thing to look into is the solver settings themselves. We have kind of three presets here. A survey simulation is a fast but less precise simulation. Default, then the tool tries to propose a reasonable transition frequency from the wave simulation over to the geometrical acoustic simulation, taking into account the geometry and the materials that you have selected. And then we also do have advanced here, where we can sort of freely control how high in frequency we want to go with the wave solver, and some other settings as well. But I think we should just use the default setting here today. It's saying it's taking around a minute to simulate that. So I hit the run button here, and I start the simulation. Starting the simulation takes a few seconds. It's spinning up a machine in the cloud, provisioning resources, reading in the geometry data and putting it on all the GPUs that are running the simulations and so on. So this takes just a few seconds, and once that has begun, we can see the simulation starting to progress. Note here, I forgot to put names on the other two sources, so we have cool source and source 1 and 2. That's fine. So note here that we will see progress of the three different sources, because actually each source is a separate simulation, but the user doesn't really feel that you don't have to run them sequentially, they just run in parallel on the cloud. And now we see that this has started. Another thing that's very neat is that because this is cloud-based, it's not running on my computer, I can just close this thing and immediately start setting up my next simulation. And I can duplicate the settings of my previous simulation, so use that as a starting point and for setting up my next simulation. Let's say here, improved material configuration, some absorption in the ceiling. Something like this. Now I have everything that I previously set up ready to go here. I'm just going to change the material in the ceiling. Let's put some glass wool into the ceiling, maybe a 40 millimeter thick glass wool, so a rather commonly employed acoustic treatment, which has some absorption, particularly in the higher frequency range. I don't need to do anything else. Now it's suggesting that I simulate a bit shorter than before because the space is a bit less reverberant, probably because there's more absorption, but I just hit the run button and I'm ready to go. And now the two simulations are running in parallel. I can see the progress of all running simulations here in the sort of overview, all the recent simulations I have run and the status of current running simulations. And now it's telling me the first simulation is actually done. I want to show you the results of the two simulations in sort of together. So while we wait for the second simulation, I can show you a couple of things here. Let's go back to the first simulation. For example, in the advanced setting here, and I'm editing the simulation so it's giving me a warning, but in the settings here I can test how long the simulation will take as a function of how high in frequency I go. So let's just take a look at that for 1 second impulse response. For low frequency simulation, it's around a minute that it's suggesting here. But if we go higher in frequency, then the runtime increases, of course, and even higher to around 45 minutes for this particular space. But we can easily, clearly cover the sort of low to mid frequency range in practical runtimes with the tool here. Second thing I can show while we wait is a support portal here. If we have some issue or need some support, then we can just open the tool here, send us a message, and you will get a response and help very quickly. Okay. Now we can see the simulation is just about to finish the second one. I'm going to revert back so I didn't modify any settings of the first simulation, and we can start looking at results. I enter here the results view, and what I'm faced with here is two charts essentially. On the left here we see all kinds of acoustic parameters that we can analyze in the space. I can of course select different sources and receivers and so on and see how this varies. I can, we have reverberation time, early decay time, clarity, definition, center time, amplification or strength, sound pressure level, speech intelligibility as a function of the background noise level in the room, and so on. I can also look at the impulse response of the room and the narrow band frequency response, which is very precisely simulated here at low frequencies, which means we can analyze the modal behavior of the space too. Another thing I think is quite neat is that we can compare simulation results. So let's take these two simulations that I've now run and compare the results from them. And we see here with the improved material configuration, of course the reverberation time in the room decreases and the acoustics are improved. We will also see this in, for example, different energy decay curves and so on. The energy is decaying faster in the room when we have better or more absorbing materials. I can hit the download results button, which downloads all the spatial impulse responses in an Excel sheet with all these parameters and so on. Okay, this is sort of the graphs and numbers part of the results, which is very useful and interesting. But what's not less fun is to actually just listen. And then I go here into what we call the Auralizer. Here I'm faced with a tool where I can create a sort of a soundscape in the model, and I can experience it and I can compare things on the fly. So here I have the three sound sources I put into the simulation, and I can select sounds from our very extensive list of anechoic sounds to be playing from the different sound sources, and I can pull in here different simulations that I've run to kind of do A/B comparison on the fly, jump between receiver positions and so on. I'm just going to demo it now a little bit, and let's listen and enjoy. I'll start with just a sort of drum loop sound. It's a nice sound because it's so kind of percussive, so you can really hear the acoustics of the space pretty well. First I'll play the anechoic sound, and then I'll jump into the room and move around and change things on the fly and so on. Okay, I now go into the room. I'm moving the head, and the spatial audio is kind of updating in real time. I'm jumping between different positions, and I can compare the different simulations, the different material configuration. And clearly it's more reverberant in this initial material configuration. Okay, let's try putting in a bit more reasonable sounds here than just a drum loop. Let's try creating like an office soundscape. So I'll put some office atmospheric sounds here, some office chatter as well, maybe some classroom background as well. That's kind of similar. I'll play that here. Increase that a little bit. I can adjust these things on the fly. We put the Atmos sounds a bit higher. Coffee machines going. And so on. So this is a way to analyze the acoustics in a more intuitive way, and also to be able to communicate the acoustics to someone who is maybe not so familiar with reverberation time graphs and so on. Okay, but let's now say that I wanted to improve the acoustics even further. I want to add partitions here between desks, and maybe this big wall here could use a wall absorber to get the reverberation time even shorter. Then let's open up SketchUp and modify the geometry here. Takes a second to start SketchUp. Okay, and I'll open an empty model like this. I'll open the Treble plugin here, and I can fetch the model that I was playing around with from the cloud, so I don't need to keep locally any files or anything like that. This was a part of the office building project of the second floor space, and let's fetch the initial design here. And I get it into here. Here is my model with all the layers that I had previously defined. Now let's add a couple of layers. One we call wall absorber, and one we call partitions. Something like this. And let's start by drawing the wall absorber here. Something like this. Be sure to put that on the right layer, like this. And then let's draw in some partitions. Now you will have to live with my mediocre SketchUp drawing skills, but let's put a partition here. Let's say it's 80 centimeters high, something like that. Maybe it goes across here. Here's the midpoint, right? Midpoint. There we go. And draw it up here, 0.8, and across. Okay, now we have our first partition. It's on the partition layer. I'm now going to copy that and paste it to the other desks as well. Something like this. There we go. And the final one. Okay. These are the changes I wanted to make. Now I can just check the model that it's suitable for simulation. It is. And then I can upload it to the Treble platform. And let's say here, now with partitions and wall absorber. Upload this thing. It goes to the cloud, and I can pop it open here, and it takes me directly to the platform. Here I have not run a simulation on this particular revision of this geometry, so it's telling me I need to create my first simulation. I can do that, but luckily I can pull the settings of my previous simulation, so I don't have to set everything up again. And let's just say even further improved, call it this simulation. And then all of the settings that I had from before are set and good to go, except for the surfaces that were modified when I was modifying the geometry. So, for example, the tables here, they were a bit modified because I was putting the partitions on, so I'll have to reassign the material there. Wall as well, you know, most of the wall surfaces are untouched, but a couple are. I'll just reassign the whole layer here with this gypsum board material. Cabinets, what did we put? Plywood, paneling. And then the wall absorber, of course, let's put rock wool, 50 millimeter, maybe with a glass fiber surface as well. And the partitions, how about if we put that to be 25 millimeter rock wool with glass fiber surface. Okay, also need to double check that my scattering coefficients are correct. The ones that were affected will be reset, so something like this, and this one here. That's it. Now I'm ready to rerun my simulation with this modified geometry. Because I haven't run a simulation on this before, I need to estimate the runtime here, or I could just hit the run button and then it would start, and then it would just first estimate and then run it, but I will show you the estimate function here. What's happening under the hood here is that a volumetric mesh is being generated of the space, the sort of finite element mesh that's used by the wave-based simulation. And here it's saying it's taking around a minute. Actually, I forgot one thing I wanted to do to improve the acoustics. In addition to the wall absorber and the partitions, let's put an even better absorber in the ceiling. How about if we put a suspended ceiling, maybe something like this one here. Suspended 200 millimeters, 70 kilos per cubic meter suspended ceiling, like a high-performing acoustic ceiling. And then it's predicting, or it's saying I need to simulate 0.86 impulse response length, so this should be pretty good. Start this, and now we will wait for 1 minute while this simulation runs, and I think we'll just edit the video to come back in 30 seconds or so. Okay, now we're coming back here just 30 seconds later, and the simulation is just about to wrap up. There will also be a little bit of post-processing of the data before we can start looking at results. Let's just see that end here. And then what I'm going to do is I'm going to compare the simulation results from the 3 simulations that I've run, 2 of which were from the sort of previous revision of the geometry, and then 1 from this one, look at some graphs and numbers, and then oralize that, and then the demo is over. Okay. Processing, processing, processing. Here it's done. Okay, let's open the result view and compare those 3 material configurations that we were testing. The 2 others, were, as mentioned, are from the other geometry revision. One we called improved material configuration, and the other one we called initial material configuration. And indeed, as expected, the reverberation time has been reduced quite a lot compared, between the sort of okay material configuration and the good configuration, and much improved compared to what we had originally. And obviously we see that in other acoustic parameters too, that the sort of acoustic performance of the space has been improved. Okay, let's now go into the Auralizer and listen to the space. So, as before, I can compare on the fly different receiver positions. I can move around the head, and I can compare different simulations, even from different models or different revisions of the geometry that I was running, as here. Let's pull in all 3 that we have run, and let's first listen to the anechoic sound, the drum loop. We get that here. And then I'll jump into the room and play a bit around. We clearly hear that the partition is doing its work, and also that the diffraction around the partition is modeled rather nicely with the timbre change that you can hear in the drum sound. And we can hear by removing the partition that the sound obviously changes. With the sort of more realistic office sounds, real quick. What's this one? And classroom sounds as well. What's the sound break? The speech source is this source here. You can kind of hear the spatialization or the localization effect pretty well if I take the head. And then I can. Okay, that was the quick demo of the Treble platform.